What does it mean for two expressions to be equivalent? So today we're going to explore graphing expressions on the graphing calculator to explore what the difference is between when two expressions might be equal to when they actually refer to the same expression. Take a look at the next page. So is 3 plus 7 equal to 2 times 5? Now, since this question is all about numbers, there's an actual truth value to this statement. 3 plus 7 is 10. 2 times 5 is 10. So those values are interchangeable. So the big idea is we can suggest that these two things are equivalent because they could both be replaced with 10, and that's what really matters. So, question 1, fill in the blank. These expressions are blank equivalent. So, what word is going to go into this blank? Okay, so let's talk about how you did. The first thing I want to do to consider whether or not these are equivalent ever is to go to my graphing calculator. So I'm going to go to my TI Inspire graphing calculator. So here's my calculator. Home screen, new document, say no to drugs, and add a graph page. So the first expression that I want to consider is 3x plus 4. So f1 of x equals, what I'm doing is taking this equation and setting it equal to the expression 3x plus 4. So what I'm really trying to do is consider every possible value of x in the expression 3x plus 4. And I get a line. Now when I press tab, it gives me f2 of x. And this time, I want to explore what happens when I put in the expression 2x plus 3. I press enter again, and notice that we get two lines that do have one point in common. So if I go through and look for where those two lines intersect, they meet at the point -1, 1. So what that tells me is there is one point when x is equal to -1. These two expressions are equivalent. And that's where I get the sometimes. So, are they equivalent expressions? From a general sense, the actual answer is no. They're not necessarily equivalent, but they can be when x equals -1. And so that's why we're going to say are sometimes equivalent, but only when x equals -1. So our next question, fill in the blank. These expressions are equivalent. So in order to answer this question, the first thing I want to do is go back to my graphing calculator. Home screen, new document, say no to drugs. And again, add a graph page. So the first expression that I'm going to put in is 5 parentheses x plus 3. So f1 of x equals 5 times the quantity x plus 3. And I get another line. When I get a new command line by pressing tab, I'm going to graph the function 5x plus 15. When I press enter, notice what happened. The red and the blue occupy the same exact line. A good way for me to look at this is to do a table, Control T. And notice as I arrow to the right, for every single input, x, so here, when x is 79, for both of these equations, our output f of x is 410. So as I toggle between those two, for every input, we get the same exact output. What does that tell me? Okay, the next question, fill in the blank. These expressions are equivalent. So again, I'm going to go back to my graphing calculator, home screen, new document, say no to drugs. So the first expression that I want to graph is 2 times the quantity x minus 7. When I graph this, I get a line like so. Now I press tab to graph the next function, and I have 2x, so f2 of x equals 2x minus 15. And enter. And what I notice here is that I've got 2 lines, and as I zoom out, I'm trying to answer the question of, are they ever equal? Okay, this time my question involves the quantity x plus 2 times x plus 3 and the quantity x squared plus 5x plus 6. So we go to our graphing calculator. Be sure to write these values down before you open your calculator. Home screen, new document, say no to drugs, and add a graph page. So my first expression is x plus 2. So f1 of x equals x plus 2. Close my parenthesis. Now here's the trick where I want to put in a times symbol, because sometimes the calculator doesn't know what I'm asking. So then I'm going to say x plus 3. And what's different about this question is I don't get a line anymore. I actually get a parabola. So now I want to test the other expression. So I press tab, and this time I need x squared. So the x key and then the squared key. You need the x first, then the squared, plus 5x and plus 6. Enter, and I get a parabola. What do those parabolas tell me? Okay, this time we have the quantity x minus 2 times x minus 4 and the quantity x squared minus 6x minus 8. So the idea here is maybe I want to check the distributive property. I want to know when I distribute this to this, do I get the final answer, x squared minus 6x minus 8. So let's check on the graphing calculator. Home screen, new document, and say no to drugs. So first, we have x minus 2 inside parentheses times the quantity x minus 4. So I set that equal to f1 of x, and I get a parabola that looks like this. So there's our first parabola. Now, a new command line, I'm going to test x squared minus 6x minus 8. Now, as I zoom out, what's happening to these two parabolas? So the reason that this response is never is because these parabolas are exactly the same shape. The only difference is this vertex is a little further below this vertex. But they go forever and ever, but they actually never intersect. They look like they come really close as we zoom out, but they never actually meet. And if we look at the table, we can see that. So if we go over, notice that when x is 0, the red graph is negative 8. The blue graph is positive 8. So they're 16 units apart. When x is 52, 2400 to 2384, they're still 16 units apart. So for every value of x, the difference in the y's is always 16 units away from each other. So those two graphs will never share the same points. So your job for this question, fill in the blank. These expressions are equivalent. You have to decide what word goes in this blank, and how you're going to do this is pause the video now and actually graph these two functions on your own. So you're using your graphing calculator to determine if these are the same graph, two overlapping graphs, or two graphs that never touch. Okay, so here we go again. This is the you do portion. This is where you have the responsibility to make the determination of when these two expressions might be equivalent. So your job, graph each function, set them equal to f1 of x, and determine what their equivalency is. So before you answer this question, I want you to pause the video now and graph both expressions so you can make your determination about their equivalent relationship. So let's examine what's going on. I've got the expression x plus 3 times the quantity x minus 4. My other expression, x squared minus x minus 12. So we're going to go to our graphing calculator. Home screen, new document, say no to drugs. And I'm going to start with x plus 3. Make sure you use parentheses. And between the sets of parentheses, the multiplication symbol times x minus 4. Enter, and we have a parabola. Like so. Now we press tab, and we're going to graph the function x squared minus x minus 12. Enter, and we have another parabola. Based on our picture, what does that tell us about the equivalence of these two expressions? Okay, so now we've got another expression, x plus 2 times x minus 5, and then x squared minus 4x minus 10. So we want to compare these two expressions by graphing them in the graphing calculator. So pause the video now, graph both expressions, and determine what their equivalence is. Okay, so immediately when I look at these two graphs, the first thing I notice is I see blue and red at the same time. If I'm seeing two different colors, that screams to me that these are not always equivalent functions. So I've eliminated the always from the get. So the real thing that I need to look for is there a point where one crosses over the other one? It's not blatantly obvious here, so maybe I have to zoom out a little bit. So when I zoom out, notice the red parabola crosses the blue somewhere down here. So I know that there is actually a point of intersection. So right there at 0, negative 10, when x equals 0, those two functions are the same. That's the only time they're the same. So therefore, these expressions are equivalent when x equals 0. So of course, our answer is sometimes, not always, not never, but when there's one specific value of x that works, we get these sometimes equivalent. So wow, we've done a lot of work here and we're at the very last question. So I want you to take your time and make sure, because these numbers are a little bit uglier, but the reality is if you're using your graphing calculator and graphing these as functions, there should be no reason that you can't determine whether they're either always, sometimes, or never equivalent. So pause the video now, graph both of these functions, and make a determination on whether they're always, sometimes, or never equivalent. So let's test what happened. Home screen, new document, say no to drugs, add a graph page. So on one side, we have 2x squared minus 9x minus 18. And that doesn't look like a parabola because the vertex is way down here at the bottom. So that's where you may have to zoom out just a little so that you get a better look at what's really going on. Now, our second function, press tab for a new command line, is 2x plus 3 times x minus 6. And notice this time, those look an awful lot alike. So based on just glancing at the picture, my instinct is to say those are the same exact graph. If they're the same exact graph, regardless of circumstance, these two expressions are equivalent. But maybe we want to take a look just to be 100% sure that we got the right answer. Remember what the word table starts with. T. So I'm going to press my red control key and the letter T. That gives me a table, and notice this table is blue. Up here, f1 of x is the blue graph. If I arrow to the right, f2 of x is the red one. So we know when x is 1, f of x is negative 25 for both when I toggle back and forth. That's one answer. I'm going to go way down here, actually grab my slider and go really, really fast and far, right? Now, when x is 123, my f of x is 29,133. 29,133. See how it toggles back and forth? That's how I know that when I go to all these different numbers, and any time that I toggle back and forth, I have the same number. What it tells me is for every input x, I get the same output y for both of these functions. Therefore, they're the same exact function, and these two expressions are always equivalent. So remember, when we're considering equivalence, they're either always equivalent, which means they're the same expression just written in different ways. They're sometimes equivalent, which means they have a point in common. We can identify a value for x that makes them the same, but only for a specific value of x. Or else, the final possibility is that those two graphs have nothing in common and they're never equivalent. So it's always going to be one of those three choices.